Good morning to all. I am Karina from BSc Chemistry Honors Second Year. Today's our topic is from Pradeep's Physical Chemistry book by Dr. S.C. Khetrapal. Our topic is Thermodynamics 2. Introduction. Need for the second law and different statements of the law. The first law of thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law, and as a consequence, some definition given to the second law are briefly given as below. A major limitation of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energies involved, but it provides no information concerning the feasibility of the process, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to a hot end or not. All that it tells is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supplies answer to above questions by stating that all spontaneous processes like the flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc. are thermodynamically irreversible. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous processes. However, it may be mentioned here that the term spontaneous does not give any idea of rate of the process, whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of an external agency. The first law states that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or the surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated as follows. The complete conversion of heat into work is impossible without leaving some effect elsewhere. Besides the above definition, a number of other definitions have also been given to the second law of thermodynamics. The two important ones are: it is impossible to construct a machine functioning in cycles which can convert heat completely into the equivalent amount of work without producing some changes elsewhere. Without the use of an external agency, heat cannot by itself pass from a colder body to a hotter body. The term functioning cycles is introduced in the above definition to indicate that the machine must return to its original state. The term functioning in cycle is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of the ideal gas, change in U equals to 0 so that Q equals to W, that is, the work done is exactly equal to the heat absorbed by the system. In other words, in this process, heat is completely converted into work. However, it is important to observe that this conversion is accompanied by an increase in volume of the gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding section of this chapter. The fraction of the heat absorbed by a machine that it can transform into work is called efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by neta equals to W upon Q. The machine used for conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbs heat from a heat reservoir at a higher temperature called the source converts a part of it into work and returns the remainder to the heat reservoir at a lower temperature called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, Sadi Carnot in 1824 devised a technique called Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in this manner is called a cyclic process. The engine chosen by Carnot, called Carnot engine for the purpose of calculation of the efficiency efficiency was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless pistons so that all the operations in the cycle are carried out reversibly. For this reason, it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a higher temperature T2 called the source and the other at a lower temperature T1 called the sink. If some operation is carried out by placing the cylinder in the source or at the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an insulating material, no heat exchange can take place between the system and the surrounding and hence the process is adiabatic. The Carnot cycle consists of 4 different operations which can be represented on a pressure volume diagram, sometimes called as indicator diagram. These operations are carried out as shown in figure and are briefly described below. Number 1. Isothermal expansion. The cylinder containing 1 mole of ideal gas occupying a volume V1 is placed in contact with the source heat reservoir at temperature T2. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work done work by 1 mole of the ideal gas will be given by minus W1 equals to RT2 ln V2 by V1. Further, for an ideal gas, the work done is equal to heat absorbed Q2 so that minus W1 equals to Q2 equals to RT2 ln V2 by V1. Here W1 has been taken as negative and Q2 as positive by latest SI conventions of sign. The second is adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3. The path is shown by adiabatic curve BC in figure 2.1. The work done W2 will be given by minus W2 equals to CV T1 minus T2, which is equals to minus CV T2 minus T1, where CV is the heat capacity of the ideal gas. Again, W2 is negative by usual convention of sign. Number 3 is isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink, that is the heat reservoir at lower temperature T1. The gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by the path CD. The work done is taken as positive by usual sign convention and hence will be given by W3 equals to RT1 ln V4 by V3. During the operation, an amount of heat Q1 exactly equal to W3 will be returned to the sink at T1, that is, heat has been given out by the system. Using the appropriate convention of sign, Q1 will be negative and W3 will be positive, so that minus Q1 equals to W3 equals to RT1 ln V4 by V3. Number 4 is adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A is regained. The temperature of the gas rises from T1 to T2. The work done is positive by convention of sign and will be given by W4 equals to CV T2 minus T1. As a result of these four operations, the system has returned to its original state so that a reversible cycle has been completed. The net work W done by system will be given by W equals to minus W1 plus minus W2 plus W3 plus W4, which is equal to RT2 ln V2 by V1 minus CV T2 minus T1 plus RT1 ln V4 by V3 plus CV T2 minus T1 equals to RT2 ln V2 by V1 plus RT1 ln V4 by V3. Since V1 and V4 lie on one adiabatic curve and V3 and V2 lie on one other, it follows that V4 upon V1 raised to power gamma minus 1 equals to T2 by T1 and V3 by V2 all raised to power gamma minus 1 equals to T2 minus T1. On comparing these equations, V4 upon V1 raised to power gamma minus 1 equals to V3 by V2 raised to power gamma minus 1, and gamma minus 1 cancels each other on both sides, or we obtain V4 by V1 equals to V3 by V2. V4 by V3 equals to V1 by V2. Putting these values in equation 8, we get RT2 ln V2 by V1 plus RT1 ln V1 by V2 equals to RT2 ln V2 by V1 minus RT1 ln V2 by V1 equals to RT2 minus T1 ln V2 by V1. Dividing equation 12 by equation 2nd, we get W upon Q2 equals to T2 minus T1 divided by T2, which gives the efficiency of the Carnot cycle or engine. Carnot theorem. From equation 13, it is clear that the efficiency of the reversible heat engine depends only upon the temperature of the source and the sink and is independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operation, because the work done in the adiabatic operation cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion from A to B is maximum, whereas the work done on the gas during the reversible isothermal compression from C to D is minimum. Hence, the total work done by the system, that is the reversible heat engine or Carnot engine, is maximum for specified conditions, and therefore the efficiency is maximum. The result that follows from the Carnot cycle as derived and discussed in equation 13 above is called Carnot theorem. It may be stated as follows. The efficiency of a reversible heat engine depends only upon the temperature of the source and the sink and is independent of the nature of the working substance. In other words, all reversible heat engines working between the same two temperatures have the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperatures. Since the quantity T2 minus T1 upon T2 is always less than unity, the efficiency of the heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined as follows. A heat engine absorbs a certain amount of heat from the source, converts a part of it into work, and returns the rest to the sink. In other words, it is impossible to convert heat completely into work. Further, combining equations 2nd, 5th and 8th, we get W equals to Q2 minus Q1, that is the net work done by the system is equal to the net heat absorbed by the system. Putting the value of W in equation 13, we get Q2 minus Q1 upon Q2 equals to T2 minus T1 upon T2. Hence, the efficiency of a heat engine may be given by any one of the following expressions equals to neta equals to W upon Q2 equals to Q2 minus Q1 upon Q2 equals to T2 minus T1 upon T2. This result, derived for a reversible Carnot cycle, leads to the introduction of a new thermodynamic term called entropy, as discussed in the next section. Thank you.